Ever stop to think about what gives metal its amazing strength? Well, today we're diving way down to the atomic level. We're going to uncover this hidden architecture that explains why some things, bend, while others just shatter.
Okay, let's start with a little puzzle. Think about it. Why can you bend a paperclip into all sorts of shapes, but if you try that with a glass rod, snap, it just breaks, right? This isn't just some random party trick. It actually gets to the very heart of how the materials all around us work.
So, the answer to our paperclip puzzle? It's not something you can see on the surface. Nope, we have to go deeper, inside the material itself, to look at its hidden structure.
Okay, so it really boils down to two main categories of solids. On one hand, you've got your crystalline solids, like metals. Think of their atoms as being super organized, locked into this perfect repeating 3D pattern. We call that a crystal lattice. Then you've got the other kind, amorphous solids, like glass. Their atoms, a total mess. It's just a random, jumbled-up arrangement. And believe me, this one difference, order versus chaos, is the key to everything.
All right, let's zoom in on that paperclip. We're going deep inside the crystal lattice to see what's really going on.
So that whole organized structure isn't just random. It's actually built from this one tiny, repeating group of atoms. We call it a unit cell. Honestly, the best way to think about it is like a single Lego brick. You take that one brick and you just keep adding identical ones on top, to the side, in front, and behind, and pretty soon you've built the entire crystal.
Now, when it comes to how metals actually pack these atoms, they tend to favor a couple of specific arrangements. In fact, most of the common metals we use every single day, think about the iron in steel or the aluminum in your soda can, they use one of two main structures. There's face-centered cubic, which we call FCC for short, and body-centered cubic, or BCC.
And this packing is, well, incredibly efficient. It's a big reason why metals are so dense. Look at the FCC structure, the one you find in aluminum and copper. It fills up a whopping 74% of the total space with atoms. That's actually the most efficient way you can possibly pack spheres together. The BC structure is a little less jam-packed at 68%, but still, that's a ton of atoms crammed into a tiny space.
Okay, so up to this point, we've been painting this picture of a perfect, orderly world of atoms. But here's the twist. The reality and the real secret to why a metal can bend, it's not about perfection at all. It's all about the flaws.
I know, that sounds totally backwards, right? But it's absolutely true. In the world of metals, defects aren't a bug, they're a feature. Seriously, these little imperfections are exactly what allows a metal to bend and deform without just snapping. And what's even cooler is that engineers have figured out how to use these flaws to their advantage.
So the most important defect we need to talk about is something called a dislocation. Just imagine that perfect crystal lattice we saw before. Now picture someone squeezing in an extra half row of atoms. But this row doesn't go all the way through the material. It just stops right in the middle. That creates this line of distortion, and that is what we call an edge dislocation.
And this is the whole secret behind bending. When you push on a metal, it doesn't have to break all of its atomic bonds at once. That would take a huge amount of energy. Instead, it just has to move this dislocation. The bonds right next to it break and then reform, one row at a time, allowing that extra half plane of atoms to just glide through the crystal. It's exactly like an inchworm trying to move a giant carpet. It doesn't lift the whole thing at once, right? It just humps up a little section and scoots it forward. That step-by-step motion, that's what we call plastic deformation.
So this really explains the two different ways materials can react to a force. If you bend a paperclip just a little bit, the atomic bonds are just stretching, kind of like tiny springs. That's called elastic deformation. You let go and it pops right back to its original shape. But if you bend it too far, you start pushing those dislocations around, and that's plastic deformation. It's permanent. It stays bent. Now you see why glass snaps. It doesn't have that neat, orderly lattice, so there are no dislocations to move. The bonds just stretch and stretch until, poof, they all break at once.
Okay, so this brings up a really interesting idea. If it's the movement of these little defects that lets a metal bend, what happens if we figure out how to stop them in their tracks?
Well, what happens is you get a stronger metal. This is the absolute core principle of metallurgy. To make a metal stronger, harder, and tougher, you have to restrict the movement of dislocations. It's not about making a perfect crystal, it's about strategically getting in the way of those moving defects. You're essentially creating microscopic traffic jams. And engineers have like a whole toolbox of tricks to do this. For one, they can shrink the size of the crystal grains.
Smaller grains mean more boundaries, which act like roadblocks that are tough for dislocations to cross. Another trick is to add different atoms into the mix. This is what an alloy is, like adding carbon to iron to make steel. These impurity atoms distort the lattice and act like little speed bumps. Or they can just bend the metal over and over. You know how a paperclip gets tougher to bend the more you work it? That's because you're creating a ton of new dislocations, and they all get tangled up with each other, creating a huge gridlock where nothing can move.
So when you zoom back out, you can really see the big picture. It's incredible. The strength of a massive bridge, or the lightweight frame of an airplane, or the durability of the engine in your car. It all comes down to our ability to control these tiny, invisible defects at the atomic level.
And that leaves us with a really exciting thought, doesn't it? We've basically figured out the atomic rulebook for making things strong. Now that we can design new materials from the atom up, the possibilities are almost limitless. So you have to wonder, what huge problems are we going to solve next?